this really a line or not? Is it really a curved relationship if I look at the data? We should think about all these things. The way to do it is by investigating the residuals. A bit like you've done already back when we tested for normality on raw data. You've tried that now. We could check normality by normality plots. That's definitely something we could do. This is, yes, check. We already did that. Now I do it on the residuals. I check for normality. So yeah, you can repeat what you've done here. And then something new today that you didn't do before. We should also check how residuals, and this is my final slide with content. I can extract the residuals from my model object. I could also compute them myself. I know the formulas. It's not difficult. But I can take them out in R, and then I can plot. I can make the normality plot. It's not the nicest version we see here, but that's what I talked about before. And then I do something new. I plot residuals versus the fitted, the line values. The fitted values is the name for the y hats. So I plot epsilon I hat versus yi hat. The deviations versus the line values. And then I primarily check for the homogeneity of variability assumption, meaning that the point cloud, it's not the world's greatest plots we're looking at here, but hey, the point cloud should be like this for the assumption to be fulfilled, right? It looks nice, roughly, like that. The one you look for typically would be the very classical shape of points in this plot that would tell you, warning, 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 something wrong. This is the classical trumpet shape. That's the most frequently occurring, type of deviation from the classical assumption. And this is a case which happens often where it happens on stock exchange data, it happens on physical data often, that it would maybe happen on the weight data also if we really dig into a big data set. Because such a deviation says that people with high centimeters, tall people, tend absolutely, potentially, to have higher variability on the weight than small people. And somehow that's physically meaningful, right? That there's less room for having a variability of 100 kilos if you're very, very small. If we go down to 50 centimeter guys, they won't have a kilo variability with 10 kilograms, right? Because they only vary between 2 and 4 kilograms, right? Whereas guys that are 2 meters tall, they might vary from 80 kilograms to 200 kilograms, right? Much larger variability for big guys than for small babies. Absolutely seen on the kilogram scale, right? So that is why we look out, typically. That's our first worry when we check this sigma homogeneity, or as econometricians call it, homoscedasticity, if you are an economy guy, the same variability no matter where we are. We'll get back to that when we do the multiple regression thing next time. We'll do more residual and model validation. It's an important part of applying these models to go check that they seem to be okay. Right, sorry for the 5 minutes above, and enjoy it out there. I'll see you